Here's my video report for Lab 3 circuits. The purpose of this lab is to observe the behavior of circuits with resistors in series and parallel, measure current and voltage using a multimeter, and examine the behavior of ohmic resistors, and capacitors. In our results, the potential difference was negative 0.938 volts for the 47 ohm resistor and negative 1.996 volts for the 100 ohm resistor. Delta V was found to be negative 0.024 volts. In our RC circuit, the 10 ohm bulb took 10 seconds to charge, 12 seconds to discharge, and with the 20 ohm bulb, it took 18 seconds to charge and 21 seconds to discharge. For some of the important principles of this experiment, there's the node rule where the current into a point is equal to the current coming out of the point, and the loop rule where the sum of all the electric potential differences is equal to 0 for a complete loop. Ohm's law is V equals I times R, and capacitance is Q equals C times V. Here's an experimental overview of our in-series circuit. The initial conditions is 2 ammeters, 2 resistors, one that's 47 ohms and the other which is 100 ohms, and 2 batteries, each 1.5 volts. The system is the circuit and the surroundings is everything else. The predicted currents that would be read at the ammeters is found using Ohm's law. In our calculations, we predicted the current would read to be 0.0204 amps, and based on the node rule, it's predicted that both current values would read to be that same value. In what we measured, both ammeters read as 0.02 amps, showing that the current is consistent throughout the circuit. Replacing an ammeter with a voltmeter, we expected the sum of all the potential differences to equate to 0 according to the loop rule. The measured potential differences across each resistor was measured, where at the 47 ohm resistor it was negative 0.938 volts, and at the 100 ohm resistor it was negative 1.996 volts. When we measured the voltage of the circuit without the resistors, it was 2.91, and summing it with the potential differences of the resistors, it equates to negative 0.024 volts. This is slightly different from what we expected, which is delta V equals 0, and this may be due to the fact that there are external forces acting upon the system that we're not considering. There's also non-idealities in the system that we're not including in our calculations. Here is an approximate graph of the potential versus the position around the circuit. In the 100 ohm range, the electric field is large, so the slope is steeper compared to the 47 ohm range, and eventually the volts go to 0 in the F to H region. So when we place the ammeter in parallel with the 100 ohm resistor, we see that less current comes into contact with the 100 ohm resistor, since the two paths can be traveled either to the ammeter or to the resistor. So the current read goes from 0.02 amps to 0.06 amps at the ammeter. Since the ammeter has no resistance, it causes the current to increase, and using ohm laws, we find the resistance at the resistor's wire and ammeter from the potential difference and current measurements. Some values are lower than expected, which may be due to the precision of the ammeter itself. Here's our experimental overview for the second part of the experiment with the RC circuit. The initial conditions, a 1F capacitor, a 10 ohm and 20 ohm bulb, and 2 batteries, each 1.5 volts. This system is a circuit and the surroundings is everything else. First, we connect the battery to the 10 ohm bulb and capacitor in series to observe the behavior of the capacitor charging. Initially, the bulb was really bright, but it gradually dimmed as the capacitor was charging until it turned off completely after around 10 seconds, where the current was 0. When we disconnected the battery, the bulb lit up again and the brightness decreased until it turned off completely as the capacitor discharged in 12 seconds. The same setup was done with the 20 ohm bulb, where we found it took 18 seconds to charge and 21 seconds to discharge. And with the higher resistance, the charge and discharge time is longer compared to the low resistance. Using the equations from the lab documents, we can create a round-trip potential plot for the 10 ohm bulb. The initial voltage is 3 volts, the resistance is 10 ohms, and the capacitance is 1F. Substituting these values into the first equation, we find delta V, and once we have the equation for delta V, we can linearize it and get our graph. According to the graph, we should have expected the discharging to happen much faster than the observed time of 12 seconds. Some similarities and differences between the models: the observed discharge time is 12 seconds, the round-trip potential plot is 6 seconds. Some assumptions made: the electric field in the connecting wires is negligible, and we neglect the external forces when performing calculations. Some possible sources of error could come from the ammeter itself not being accurate, and we're also not considering the other forces in the surroundings. Human error is also a possibility, with us not properly positioning the probes to take measurements and recording the time in an accurate manner. So in our discussion, what if you charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? In our ideal model, we would predict the capacitor to reach full charge instantaneously with no resistance. In real life, this prediction would not happen because there is no such thing as zero resistance. Even with the wires, there is some small resistance associated with them. And when we used the ammeter to measure how long it would take to charge the capacitor, it took around 6 seconds, which is longer than what is predicted in the ideal model.